Hi everyone, the paper I will share today is called Linear Time Demonstration Selection for Inconnex Learning via Gradient Estimation. I'm Ziniu Zhang. I'm a second-year PhD student in Northeastern University, and this work is under the collaboration between Zheng Shuo, Dongyue, Lu, Jennifer, and Hong Yang. So in this paper, we studied the problem of inconnex learning. So inconnex learning has emerged as a paradigm for solving and generating natural language tasks using language models. And what we study is how to select a fixed size subset of demonstration examples given a query set that makes the performance best. So there are several previous works working on this before. Some of them may select the most similar demonstrations based on their input embeddings, such as they compute their cosine similarities or compute the different distance in the embedding space, but it overlooks the model output condition on the demonstration labels. Or someone may consider the output loss of different demonstrations, but if the number of demonstration set is very large, compute the output for each demonstration is very costly. So formally, our problem is our objective is that given a demonstration set, training set, and a query set, how can we select the most valuable data points from the demonstration set that improve the query output most? And based on the literature, we propose GraphSeal. So first, we consider the outputs of language models, while we use a first-order Taylor expansion to efficiently estimate the inference result. Then, based on this, we utilize the random ensemble method to select the demonstration data with the best attributions. So first is the estimation part. So consider the model output of a prompt subset S on an input query X. We can denote this as the FW. So FW is the output of the model, and given an anchor prompt S0, the first order approximation of FW around the embedding vector phi is like this. So the point here is that we compute the gradient with respect to the embedding of input. And to evaluate the accuracy of this approximation, we calculate the relative error. So we design the input prompt that vary the distance, the embedding space distance, up to 40%, and test the output estimation error, relative error on DeepSeek 7B, Llama 13B, and CodeLlama 34B. So even the distances arrive 40%, the estimation error is still very low, so around 1%. And also, we use the real data sets, such as poem sentiment, age existence, CR and modular addition to check the error, the relative error. So they are still very low. But so note that someone may consider that when the size of the language model rise, the error may rise, but from the result we found that the error is still very low, even the parameter size is very large. So the second part of our method is a kind of random ensemble method. So this random ensemble method is inspired by the literature on inference functions and the work of task affinity group. So we first draw m random subsets from demonstration set and each of fixed size k, and then we estimate the FW for each of the subsets. Then we compute an attribution score for a demonstration that equals the average of Fw over subsets include theta I. So here's a small example, and we compute the output given theta 1, theta 2, theta 1, theta 3, and theta 2, theta 3. Then we compute the attribution score using this. So to evaluate our method, we first given a case study of basic linear functions. We use examples from of learning linear functions from transformer models. And suppose that both the inconnex example and the query example are generated using this formula, and the input vector xi is randomly sampled from a normal distribution with the dimension is 20, and the coefficient vector is randomly drawn from a finite set. Here, the number of beta is less than d. So different inconnex examples may have different coefficients. And we consider two settings for the noise term. The first one is linear regression with the noise is 0, and the other is noisy linear regressions, and then we add a normal distribution noise in as epsilon I. So we first test the approximation accuracy, and in both settings, the linear setting and the nonlinear settings, our method can accurately estimate the true outputs of in-connex learning. And as k increase, the trained transformer learns the linear function correctly, and the error decreases to near 0. Since d equals to 20, so we plot k equals to 20 here, and if k is less than 20, it is nonsense. Then we test the random ensembles method. To further evaluate the random ensemble mechanism, we report the average score of demonstration samples from beta 1 and beta 2, and the query set is generated from beta 1. So in our assumption, the output or the score of samples from beta 2 is it should be higher. So the score here is kind of the loss. So this is auto distribution data, so the output should be higher. And from the chart here, we see that it's indeed higher for auto bit distribution data. So this is the efficient accuracy of our method. And so consider the first part of our method, the Taylor expansion, first order Taylor expansion. You can utilize to other inference based selection. So we can adapt it to forward selection and cross entropy based selection. Here's the main results. We use different kind of data sets and different size of models and some latest baselines. So regarding the estimation and efficiency, we report the relative error between the estimate loss and the true loss, and then we compute the flops on one A6000 GPU card. Then here is the main results. We can find the ICL grade RE, our random ensemble method achieve the lowest flops and the lowest error. And we also consider a long context setting. So our method achieves the similar results, much less input tokens than traditional method like TalkK and the RandomK. So in summary, we first utilize a first order approximation to estimate the output of language models. Then we use a random ensemble method to compute the data attribution score. And we test our method on simple functions and real-world datasets. And thank you for listening. And this is the paper, code, and our email. Thanks.